All right. Today we are going to talk about learning the parameters of the graphical model in the presence of unobserved random variable. If you remember in the last two sessions, we talked about learning the parameters when the structure is known, but all of the random variables are observed. So we talked about two different scenarios, fully observed Bayesian network. And we talked about the case that basically when the fully Bayesian network is when Bayesian network is fully observed, the maximum likelihood decomposes into set of independent optimization. So and then we decompose it basically so that a method of choice for modeling the marginals and also conditionals are generalized linear model and exponential family and generalized linear model. To recap the exponential family, if you remember, the exponential family was where T was the sufficient statistic, theta was parameters, A theta was log partition function, and H was a set of other terms. It's called base measure, and it was independent of theta. We talked about maximum likelihood estimation in the context of exponential family, and we said that so basically partial of A with respect to theta is going to be expectation of the sufficient statistic. We also mentioned that A theta is positive definite, and second order become covariant, and so on and so forth. We also talked about generalized linear model. We draw this graph of parameters and features. Basically, was to model this case, and that when they multiply together, they are going to model a function of basically they're going to model a function of our mean, and the mean was connected to A theta. To theta through inverse, and there was a link function also here. Hopefully you guys remember this part. And then we mentioned that if we have a fully Bayesian network, so the maximum likelihood of the entire thing is going to be maximum likelihood for each of these terms. We also mentioned UGM. The UGM things was slightly different because in UGM we have this form of multiplication of all of these factors. Multiplication of, so C is the factor of the variables, and theta C was the parameter of the factor C. And we mentioned that maximum likelihood is more complicated because they are coupled through Z theta. So, but in both of these settings, we didn't talk about what happened if some of the parameters are observed. So we assume that everything is observed. So today we are going to talk about that. So overall, there are few principles for estimation. Maximum likelihood estimation is one of the most common one. We also said that, well, sometimes you want to view the parameters, you want to assign the distribution over the parameters and compute the posterior. That's more like a Bayesian approach. And we also mentioned very briefly something about maximum entropy estimation as another principle of estimation in graphical model. So if you remember this slide maybe 2 weeks ago that I mentioned that inference, you have exact inference and approximate inference. We talked about variable elimination, message passing. We said that, okay, so this is for simple graph. You can deploy it. As the graph gets complicated, you need more approximation method. And we are getting close to basically this section of the talk, because when some of the variables, we are not talking about it today, we're going to talk about it in the following weeks. But we are getting into approximation because if some of the variables are unobserved, you have to resort to some sort of approximation that we see today. So now, okay, so let's start with an example. Let's say that somebody has given you a voice over the phone and you want to parse it to see what this guy is saying. So you want a level of a model that listens to the voice and transcribe the voice into sentences. So you're going to partition the voice into a window, and you want to see what each of these windows correspond in terms of like layers. Like, is it W? Is it A? Is it B? And also, of course, you have to incorporate the smoothness between variables because A most of the times follows by E, and I don't know, rarely follows by X. So you want to incorporate that into your graphical model. So you need some sort of like a smoothness. One vanilla version of such model is hidden Markov model. So where the X is these features that you extracted from each of these windows, and the unobserved random variables are Y's, which represent each of these letters or alphabet that you want to decode. So you're assuming that that letter, when it's pronounced by a person, manifests itself into a wave sound, and you extract features from it. This is observed, and these are unobserved. So this is an example of when you want to infer something that not everything is fully observed. Another example, let's say that you get the genes of set of species, human being, mouse, and then you know that all of these have the common ancestors. Although I'm making a lot of simplification, they're all coming from bacteria, and there is the tree that each of these go through evolution and evolve and become different species, so you can view it as a tree. And it takes, let's say, millions of years to go from one species to another species, and there are a set of ancestors in between that are unobserved because they got extinct or whatnot. So we don't know how much it takes from that unobserved, the genetic profile of that unobserved ancestors, and how long it takes from that to evolve and makes a human or mouse or something. And but you want to model it as some sort of like a tree structure. So this is another example. Perhaps the most familiar example of that is simply density estimation. So let's say that I'm giving you this sort of data point in two-dimensional. I'm telling you, can you do density estimation for that? So one assumption, one relatively valid assumption would be that, well, this is not a unimodal distribution. Let's assume that the way that we generate this data is that we first say that which mode it should come from, and then we randomly draw from that distribution. So, so basically, there's a way to do the density estimation for the entire observed data. So there might be some meaning behind each of these unobserved modes. For example, it can be representation of the specific hormone in male versus female or anything else. It might not have a meaning. But that's a way that we model our density. So the way it works, for example, in this specific case is that for each observation that here I'm represented by X, there is unobserved random variable that says that which mode of distribution this data belongs to. I haven't observed that. So, and given that I have a noise that's so I add a noise based on the distribution of that mode. So, for example, if I assume that there are 4 modes here, so these data, so this is mode 1, 2. This is mode 1, 2, 3, 4. So these data, the z of this is coming from mode 1, and the z of this guy is coming from mode 2, and so on. So, but of course, I haven't observed it, and that's not a unique way of. This is not the only way of modeling this, but we are going to go with this model because it's a good example for the rest of the course. So overall, as I told you, what are these unobserved random variables? Sometimes these unobserved random variables are some abstraction, some simplification of something that we do not have access to. And but we don't have any way to measure it. For example, in this example that I told you, that there might be some ancestors that we don't have, which is they got extinct, and we don't have DNA of that, but we can, based on the partial data that we have, we can infer it. Sometimes they might have some real world meaning. For example, unobserved cause of the disease, or something else, that there is a real meaning to that, but unfortunately, because either it's very risky or it's very expensive, we don't have access to direct measure. Also, it's possible that it is something that we measure, but our measurements are noisy. For example, the real temperature of this room, if I don't have very fancy machine, I just, let's say, use my I don't know, like cell phone that gets report from Google, and I want to measure the measurement, the temperature of this room. It can give me the temperature of Pittsburgh or maybe areas around CMU, but it cannot give me a measurement of the actual measurement of the temperature in this room. So you can use that as a noisy measurement of the temperature in this room. So these are the examples. Of course, unobserved random variable can be discrete, can be continuous. For example, if discrete can be, for example, represent the partitioning of the data, which mode this data belongs to, or which gene specific, which gene, for example, enzyme is driven by, and so on and so forth. And a continuous, these are just an example. And a continuous random variable also, you can view it as a factor. It's sort of like continuous contribution of something unobserved to something that we have observed. So you can view it, for example, in the PCA type of setting, you can view it as a latent loading of each of these factors that we haven't observed. So these are just an example of unobserved random variables to give you an idea of when you want to model what you can put in unobserved, what you can put in observed. So you're going to go over some of these examples in the following. So let's go back to our favorite example, which is good example to start with, our mixture model. So let's say that I'm given very simple data set, which shows on the right. And these are data point on two-dimensional, and it obviously looks that's coming from three modes, three distribution, because there are 3 bumps. And I want to model it. I want to generate more sample from it. This is the data I've given, and somebody asked me that, well, this is the data, generate 1,000 more from this. Of course, she has given me only this data set. She hasn't given me the modes of this, and this is a very simple scenario, but let's start modeling that. So one way of modeling is that I have some observation, which is the coordinate of this point in two-dimensional, and I have some unobserved, which basically tells me which modes of the distribution each of these data points are coming from. So I'm going to use some categorical random variable z to indicate that each data point is coming from a mode. I don't know what it's from, it's unobserved. And so based on the data choice, for example, you can say that it's coming from this one, it's coming from this one, or it's coming from this one. It's going to choose between one of these. And after that, each of these modes are selected, I'm going to draw from this unimodal random variable, so which can be very simple. So, what? All right, interesting. So I'm going to fill the rest of it. All right. I don't know why it's not showing, but it is what it's supposed to be. So if I write the joint distribution of this modeling type of approach, this is what I'm going to get. So it's going to be, so let's say that each of these modes, I'm going to model it as a normal distribution with the variance mu k and sigma k. And so pi k is going to be proportional of the chance of time that I'm drawing from each of these modes. And
it's going to be
what?
Like I'm going to draw from mixture 1 over.
So if I integrate out z, so the mixture model can be modeled like that. So it's going to be proportion of distribution from, so if let's say that the k is equal to 3, so this k is going to go from 1 through 3.
Right.
And pi k is the proportion of the time that I'm going to draw from each of these. So pi 1 through plus pi 2 plus pi 3 is equal to 1. So it's a proportion of the time that I'm drawing from each of these modes. Okay, so this is if I integrate everything. I see there is no z here. I'm integrated z out. And you will be surprised that even such a simple model has a lot of application. Showing one of them here. All right, so funny today. It's not. Okay. So as I told you, I'm going to, for each of these observed point or coordinate in two-dimensional, which I represented by xn, which is observed. I'm going to have unobserved random variable that I'm represented by zn, which is categorical, coming from this k distribution. Of course, the categorical distribution we talked about is an exponential family. Is one way of representing that is as follows. That is a proportion of each of these distribution, each of these modes. And if I choose, let's say, mode k, I'm going to use the parameters of the mode k to draw randomly from that mode. So if zn is equal to k, which is coming from mode k, I'm going to draw from multivariate distribution. Is the setup clear? This is my data generation scenario or story. First, I'm going to draw from z, which tells me which mode, and then whenever that mode is specified, I'm going to go and pick one of these. So if, let's say, the zn is equal to 1, I'm going to use mu1 sigma 1. If zn equal to 2, I'm going to use mu2 sigma 2, and so on and so forth. Okay. Now, so what would happen if I integrate z out? Because if it is unobserved, I'm going to get basically, it's like, I'm going to get basically the same distribution that I told you earlier. So this is very simple, of course, very simple example. But one of the problems here is that although this is coming from exponential family, this is also coming from exponential family. When I integrate z out, this is not exponential family. There's no way that I can represent these as x theta t t x minus a theta hx. Basically, the problem that happens is that, of course, I can exponentiate and make a log, but there is no way that I can decompose it in a term that is only x and a linear function of some sufficient statistic and parameters. So, what can we do? So let's see. Let me give you first one example that why it is hard. I don't know why today none of these parameters show up in my computer, but it doesn't show up. So I'll tell you what it is. So the way that we have some problem here is that if everything was observed, I could have written log of the joint distribution as let me see why it's not working. Okay, it's working here, but not in my tablet. I don't know why. Anyways, so let me fix the recording.